So welcome to all of you who are on Zoom, and also to those in the room. I'm Professor William Green, and about 20 years ago, I was the person who got this thing started and decided to make it an open source project, which turned out to be a good idea in retrospect. All right, so I'm going to just give a few slides that are about an introduction to RMG. And then we'll have many other slides for the next update. First, about what is RMG for? What's the purpose? The RMG's aim is to predict the reactive chemistry of any given system by automatically determining all the species and reactions that are important under the specified reaction conditions, and providing all the numbers that you would need to make a kinetic simulation. And that's a pretty bold aspiration to be able to quantitatively predict such a complicated thing. Another way to look at it is RMG is aiming to reduce the human effort that's needed to construct a kinetic model, and therefore make it more practical to build good models, particularly for pretty complicated systems where it's challenging for the human to do it all. The current version of RMG is particularly useful and well tested for pyrolysis and combustion chemistry, but it can also be applied to other systems, and it has been applied to a lot of other systems as well. For example, gas surface catalysis, liquid-phase systems, atmospheric systems, different kinds of laboratory experiments. So it's a predictive tool. The reaction mechanism generates a predictive tool, and it generates a reaction network. So you see a picture there on the right of a reaction network, and that one's the fuel JP10, and the way it pyrolyzes and degrades into smaller molecules when you heat it. That picture shows that some of the arrows are thicker and some are thinner, and that's to give the idea that certain rates are a lot higher than others. So, you have the major products and you have these kind of minor side channels. So RMG is going to construct that whole model, not just the species you see, but actually there's many of these are bimolecular reactions, and there's free radicals and all kinds of other stuff involved as well. And RMG is going to estimate all the unknown rate coefficients and all the known thermochemistry and also other parameters that are needed to make a full simulation. It's an open source package. That means that you and anyone is welcome to make contributions, to fix bugs, to help extend the features, and very importantly, to expand the data set. So the reason why RMG is really good for pyrolysis and combustion is because a lot of people have used it for pyrolysis and combustion, and they added a lot of chemistry that's relevant to pyrolysis and combustion. But if you're interested in something else, suppose you're interested in reactions of tin, you could add all kinds of reactions of tin and details about tin, and then RMG would be able to do tin as well. Right now, can't do tin, sorry. So if you're interested in tin, you have to add it yourself, but it's possible to add it. In addition to building the model, the RMG software package includes a lot of tools that would be helpful to kinetic modelers. So, for example, tools for building, solving, analyzing kinetic models for many different kinds of systems, all kinds of databases and estimation methods to estimate all the numbers that are needed in these big models. And the three manuscripts cited at the bottom are the kind of key manuscripts about the overall vision. So there's the Gal paper is the paper introducing the Python version of RMG, which is the modern version. The newspaper is like the second paper about that. It's like the next improved version. And the Johnson paper is all about the estimation methods and the databases associated with RMG. Why do we need automatic mechanism instruction? You may know that there are some groups that don't do this at all. They do it all by hand. So they write lots and lots of reactions down by hand, and then make kinetic models. And some of those groups have been pretty successful. So it's possible to do it by hand. And you want to write down detailed models because then you can use the law of mass action if you have elementary step models to estimate all the rates of all the reactions. If you write down lumped models or models that skip steps, then you generally don't know how to estimate the rate rule for those reactions. And then you can write down the reaction and you know what the products are, but you don't really know what the rate is. And unless you've done some experiments, you typically wouldn't know. But if you write it down as elementary step, you know the rate law right away, and you only need the rate constant to get the number you need. And rate constants can be computed by quantum chemistry. So basically you can do any reaction if you do an elementary step. However, if you write down all these elementary steps, you get a lot of steps. And so the models get really large. And so this plot shows some published models by different groups. And you can see that the ones in the upper right corner have more than 1,000 chemical species in the model and more than 10,000 reactions. And these are all models actually for just single, like the combustion or pyrolysis of a single molecule. And you get so many intermediates and so many side channels, you just get a vast number of reactions and species. And so this is actually what motivated me to work in this field to begin with. Was I was writing them by hand, and I said, this is really tedious. Can we get a computer to do it? And it turns out that it's not just to save you the tedium, but actually you can make it better by doing it with a computer, because the computer is more consistent than a human. And also, many people were not patient enough to do a 10,000 reaction mechanism, and so they just won't do it. But if you give them a tool that does the 10,000 reactions for them, then they might open up that possibility that they could model their system. So the ultimate goal is that you're going to be able to quickly and automatically construct the chemical mechanism for basically any system that you're interested in, and the predictions of that mechanism will be accurate. That's the goal. But this raises up a huge challenge right from the beginning. You have to decide which reactions you're going to include in the model. And this is not trivial at all. So the figure on the left illustrates the problem. You can see that I have some of the species and reactions in dark, and some of them are grayed out. And so the species in dark are what most people would think are important reactions in the pyrolysis of propene. So if you put some propene in and you heated it, almost everybody would expect you'd need to have those species, and you'd have those guys and those reactions. But there's many other reactions you could imagine could be happening inside the propene system. And some of them are drawn with these dashed lines leading to the grayed out species. And unless you're brilliantly knowledgeable about the chemistry of propene, you probably would have no idea which of those many gray reactions are actually important at your reaction conditions, and which of the species. And then this is not complete at all either, because if you make, for example, the species at the top, that's a free radical. That's not going to be the final product. So it's going to go and do some additional reactions and do something else. So actually this goes on and on and on. And so it's not at all trivial to figure out like what species should be included. The way that we do this, actually the way that everybody does it first, is you list all the reactions using reaction templates. So that's in green there. So you have different types of reactions that can happen. For example, H abstraction reactions, beta scission reactions, addition reactions to multiple bonds. And so people have templates for all the common reactions, and RMG has them too. RMG will apply them to all the species in the model and get a list of like all kinds of reactions that you can make with these reaction templates starting from those reactants. And that makes a lot of possible products, a lot of possible reactions. But then there's too many, and you can't afford to include them all in the final model. So you really want to select which of those are important enough that you should pursue them and put them in your model, and which of them are negligible and you can leave them out. And the way RMG does that is we use lower accuracy estimation methods to estimate the rates of all these dashed line reactions. And if the rates are really tiny, we say it's negligible, and when we cross it out, we erase it. And therefore we can keep the size of the model under control. Now, a key issue here is the definition of what's important. You want to include all of the important reactions and important species, but what is important? When you're just starting with a bare slate and trying to write down a mechanism, it might not be obvious to you which of the many intermediates and which of the many reactions are actually important. And this actually depends on the rate estimates, on the concentrations of the species, and also on the reaction conditions, on the observables that you care about as the user, your purpose of your model, the error tolerance you have in the things you want the model to predict. All of those things will affect the decision about what's important. And RMG does it one way, actually more than one way. RMG does it some different ways, but you might think of some other ways to do it, because this is not a solved problem about how you write down the correct reaction network. Then once you have the reaction network, you need a lot of numbers. You need estimates of the rate coefficients, estimates of the equilibria. If you have a system with more than one phase, the liquids, you need estimates of solvation, kinetic solvent effects, vapor-liquid equilibria if you have a two-phase system. If you have a gas-phase system, you have to have estimates of the pressure dependence of the rate coefficients. If you have a system that's inhomogeneous, you have to have estimates of diffusivities. Many, many numbers. And if you have 10,000 reactions, you have like way more than 10,000 numbers that you need. And typically you would not be able to get them from experiment, and you actually would not be able to afford to do the quantum calculations for all of them. So you're going to have some of the numbers are going to be lower accuracy from estimates. And RMG includes many, many programs that are designed to make estimates of all these numbers, and then fill them in, and then you have a model. The RMG estimates in general are really fast, so we can estimate 10,000 numbers, no problem. However, they're not guaranteed to be accurate. And of course, if you're making a model for a system you care about, you want all the numbers to be as accurate as possible. So you can get more accurate numbers from experiment, and that's one source of good numbers. It turns out that experiments are kind of tedious and slow, and sometimes it's hard to measure what you want to measure. And so in RMG, most of the high accuracy numbers actually come from quantum chemistry calculation, which in the last 15 years have become faster than experiment and almost as reliable. But at the time you build a model, typically by Murphy's law, the reactions that matter the most to you, no one has ever measured and no one has ever calculated. So you're stuck in the situation, you have no idea what the higher accuracy numbers are. But if you could somehow get the higher accuracy numbers, there's ways you can put it into RMG, so the RMG will automatically include those better numbers in your model, and use those numbers instead of an estimate, or even use a number to improve the estimates of other reactions. We'll talk about that later. But this whole concept, you can see, now relies on quantum chemistry. And now it's important to mention that there's a lot of different levels of quantum chemistry and different approximations used to get quantum chemistry numbers, and they really differ from each other. So the 4 boxes here show 4 different quantum chemistry methods for calculating the same thing. And what these are showing on the x-axis is the error from the experimental truth of the thermochemistry of a bunch of small molecules. And the orange lines are showing the deviations. Here, orange plots are showing, it's like a histogram of how many molecules are off by how many kcals. If you look in the lower right, you can see the legend. So each tick is about 2 kcals per mole. And what you can see is that DFT, B3-LIP, which is a method you probably heard of, it's a pretty convenient method. It's really inaccurate. So you can see how broad that orange spread is, that the errors are all over the place. And basically, you have errors bigger than 10 kcals per mole very commonly if you use B3-LIP. So B3-LIP is typically not good enough for computing, for example, equilibrium constants. So we use higher level methods. For many years, my group's primary method has been CBS QB3. That's the bottom, the lower left box. And you can see that that one has smaller errors than B3-LIP in the orange. And when you correct them with bond additivity corrections, you get the blue distribution. It's actually really quite excellent. So that's why this one method is actually good, is its errors are systematic and be corrected by bond additivity corrections. On the right are more expensive, more modern methods, which are more accurate. So you can see that the orange peaks are much narrower, the distributions. So the numbers straight out of these higher level methods are much closer to the truth. And then you can also correct them and get really, really excellent predictions. That's the goal. However, those methods are really expensive to calculate. and only became possible to calculate within like the last 12 years. And even today, we have a lot of trouble to calculate things we want, and so we are forced to use more approximate methods. But you can see the improvement over time. So the DFT upper left V3 lit, that's I think 1998 was when that was invented, if I remember correctly. And the methods on the right were invented like around 2008, like 10 years later. So in 10 years, you can see how much the errors narrowed. And it's reasonable to expect that the errors will continue to narrow as the quantum chemists keep working on developing better and better methods. Actually, just two more comments. How accurate is accurate enough? This is related to the question of what's important. It depends on the temperature. You want the error in your energies to be smaller than RT. And so that's a very tight limitation at low temperature. At high temperature, it's not that hard to achieve that. And then also depends on the sensitivity of the system. Some systems are not very sensitive to rate coefficients, and you change them, you still don't get much of a difference. And other ones are super sensitive. And so it really depends on your particular system. Okay, how's RMG work? So you give it the inlet conditions, you give it some libraries, you give it the tolerances for your errors, you tell it when to stop, and you get a kinetic model. And then you can solve that kinetic model using tools in RMG, including RMS, or you can solve it by exporting the model and then feeding it into Chemkin or Kentera or other software. And RMG starts with your guess of what the initial reactants are, and it applies the templates to generate all different kinds of reactions that can be made from those reactants. And you can see there's quite a lot. And then it picks which of these reactions are actually important enough to put into the model, and it puts some of them in. So here it decides this reaction is important, it adds those two to the model. Then it adds some more, it keeps adding some more, it keeps deciding again, it recomputes the rates, tries again and again. And finally, when it hits the termination criteria for this case, the model was 42 species with almost 600 reactions. It's a pretty simple react system. And on the edge, that means the species that never made it into the model, there was an additional more than 700 additional species and an additional more than 1,000 additional reactions that were judged by RMG to be negligible compared to the termination criteria, the tolerances. And so that's a typical case that typically what's left in your model is much smaller than the number of reactions and species that were considered by RMG. So RMG had to estimate numbers for many, many, many more reactions than the actual number of reactions that appear in the model. So for example, you make a 10,000 reaction model, typically RMG would estimate more than 100,000 reactions to get there. These are the templates. These are like different kinds of rearrangements of atoms. RMG has about 80 different templates in it that represent a lot of different possible reaction types. And then we do the flux-based species selection, which is based on the estimate of the rate of the reaction. The pros of this are that you only include the reactions and species in the model that are formed at significant rates. And you don't have to make any guess ahead of time. You don't need to know anything as a user. You just tell the computer, please find all the ones that are not negligible. The con with this is it's very sensitive to the estimates. And if you have a problem in your estimator, you're also going to have a problem with the structure of your model, because it's going to either include the wrong species or ignore species that are important. And I would say this is a pretty good method. It's lasted for a long time, 26 years or so, I think, since we invented it. But it's definitely not perfect. And we have a lot of examples of cases where this method of selecting species has not found every single important reaction or species. So you should just be aware, there's no guarantee you're going to get them all. Okay, so RMG is basically taking quantum rates, building models, and then making predictions, say, of concentration profiles. And then you can see inside it has a lot of things. It has databases, it has estimation rules, it has group contribution methods, it has this whole selection thing. It also does uncertainty estimates, it has some stat mag, and eventually you get all these numbers. And this is group contributions. That's what one of the most common ways to do estimates for thermochemistry. We also have estimates for reaction rates. We did it by classifying the reactions by a tree and then picking estimates for each node of the tree. We've done a lot of different molecules in the past, and many more than what I show here. And RMG today is really quite good for combustion and pyrolysis. If you're doing those kind of problems, you should expect that RMG could be able to build a model for you that works. Sometimes it works for other types of systems, sometimes it doesn't. You'll have to, it's more of an exploratory. The RMG can build quite big models by human standards, but it's not hard to find systems where you need even more reactions than RMG can handle. So it's not like a guaranteed panacea. It's really pretty good for quickly seeing what are the major reactions happening, particularly at low conversions. Based on current knowledge of chemistry. If the current knowledge of chemistry is wrong, RMG is going to be wrong. It's just like artificial intelligence. It's not really that intelligent. It's just reproducing what you already know. Okay, and that's what it is. And you'll see discrepancies sometimes between the model predictions and experiments. And you should think of that as a positive thing, that that's showing where we can learn more, where the current knowledge is insufficient to understand chemistry. And the things that are predicted correctly, you don't need to spend any more time on them because that's already well understood. Why aren't they perfect? There's kind of two main kinds of error. One I call mechanism truncation error. It's that your mechanism is missing reactions in species it should include. So you somehow truncated your mechanism and you have an error because you truncated it. And there's a lot of different reasons why that might happen. Another possible reason is you actually have the correct reaction network, all the correct species and reactions, and you just have the wrong numbers. You have the wrong rate constants, you have the wrong equilibrium constants, and therefore your predictions are not accurate, but it's just because the numbers are wrong. And this one is very common in low temperature simulations in RMG because it really needs very high accuracy for the energies to get good predictions at low temperature. The two errors are a little bit coupled because the way we decide importance is based on the estimates. So if the estimates are wrong, estimates that are used to make the parameters are wrong, then also our species selection will be wrong. Also, if we truncate a reaction and leave it out, we're never going to spend any time calculating it or paying attention to it, even if it's important. So that truncation can also lead to pretty big errors. And for a nice discussion of that, you can see the citation at the bottom. There's a long chapter about it. Come on. You guys from Brown?
Yeah.
Hi, welcome. Yeah. There's a couple of seats at the table already. We try to reduce the errors. We use an iterative procedure. So first you build a model with RMG, just as I described. So that's the first thing to do. Okay. So you have your input reaction conditions. You say what I care about this system at this temperature, this pressure, this starting material, this time scale. And I feed that in, and RMG will follow your things, use its estimates, and make a model. So you could just go ahead and blithely go on and use RMG to do design and compare with experiments. But we would recommend don't do that. Instead, what we recommend is do sensitivity and uncertainty analysis on your model. And what you'll identify are what are the important numbers in the model? What are the important reactions for the important species? And then try to get better numbers for those because the RMG estimates are not that great. And so you get better numbers, therefore you'll have better numbers. And then you can either just take your model with the better numbers, or even better, you can feed those better numbers back into RMG and say, please build me a new model now using better numbers, not just the old estimates. And you'll get a better model. And then you can iterate this where you do sensitivity analysis on the new model. And you might have to do this again because there could be some additional reactions to species that turn out to be important now that all the numbers have changed. And you iterate this a few times until you get tired and you say, okay, now I think my model is good enough. And then you would go and compare it to some experimental data you have. And if it matches that experimental data, you'll say, oh, this model is great. Now, be warned that just because your model worked to match one experiment does not mean your model is great, okay? However, it's very difficult to prove that a model is great. It's actually much easier to prove it's wrong, right? If you prove it's wrong with the one case you try, that's a good warning, like don't just use this model. But if it's right, you know, you have to make your own judgment, and often you're very limited by the amount of experimental data you have, and also the conditions that you can measure the data at. So you might want to use the model, often you want to use the model at conditions where you don't have any data. And so you're forced to make an extrapolation with a model. Now, the fact that the model is physically based and all the numbers are physically based gives you some confidence that it might be right, but there's surely no guarantee. So just be aware. But anyway, if you do this procedure, we have some examples where this actually works. Just a historical note, from the 1970s, it was recognized that some kind of computer-aided mechanism construction was going to be needed. And it happened in around 1979. I think 4 different groups published papers showing that it was possible to use the computer to build kinetic models. However, they were the first ones, and none of those programs were good enough that they've survived. So they were just like, you know, somebody published a paper, went somebody's thesis, and that's it. However, that work in the 70s inspired people in the 1990s to try again. And in the 1990s, this much better software was made. And there's 2 programs, NetGen and XGAS, that I'm aware of that were made in the 1990s that are still widely used today, still running programs. So that's pretty good to last for more than 20 years, almost 30 years as a working program. I was a part of the NetGen development, and when I came to MIT, we decided that NetGen was not really designed properly. And so I had a student who was really good at computer science named Jing Song, and she started in 2002 creating RMG from scratch, written in Java. And she just tried to decide it for maintainability and extensibility to make it easier to add more chemistry. The previous codes really were not designed well for those 2 things. And also, we made a crucial decision to make it open source from the beginning. And also in my group at the same time, we were doing a lot of quantum chemistry calculations. And so we were able to get a lot of parameter estimates that at that time were not accessible to most people, because it was kind of new to use quantum chemistry to calculate the stuff. And we focused a lot on quantitative accuracy, which was also not always what the goals were of other people who were building these kinds of programs. And so this turned out to be pretty good. And in around 2010, Richard West and one of my students, Josh Allen, as a Skunks Work project, decided to write a version of Python. And the purpose of that was just to make it easier to develop. So Java's not that bad, but Python's even easier to develop in. And from about 2016, we stopped working with the Java version, and we switched fully over to the Python version. And that's the Connie Gao paper, reports that Python version. Since this time, several other groups in industry and different universities have built software packages that are somewhat similar to RMG. And some of them are pretty good. But I think very few of them are publicly available. They're mostly internal tools for the groups. And sometimes the industry groups, they don't want to use RMG directly and be part of an open source thing. They want to have their own private stuff. But a lot of times they'll copy a lot of the things that are in RMG. And there's also some other packages that have been written that are not really aimed at trying to get quantitative predictions, but instead to be like idea generators for people trying to guess what mechanisms are. There's these programs you read a lot of papers that's like Chemkin and Kintera mechanisms. That's actually not correct, really. There's the mechanisms are not generated by Chemkin or Kintera. Those guys take mechanisms as input. Chemkin, for example, provides a library of some mechanisms that people have made some other way as inputs. And so people sometimes just download those and use them. But really, they shouldn't call them Chemkin mechanisms. They should call them whoever made the mechanism somehow. Chemkin is just one way to solve a mechanism during a simulation. And RMG can make mechanisms. You can simulate doing Chemkin or Kintera or whatever you want. Okay, schedule. Day 1, we just did the introductory remarks. Now, Jackson, I think, is going to tell us about RMG installation and using Docker. And then we'll keep going on with a bunch of talks until lunchtime. Then more in the afternoon until about 4 o'clock. On day 2, We have these things. If you see the colors, we recommend everybody go listen to the black ones. If you're interested in the quantum aspect of improving parameters, the purple ones are good. If you're trying to be a serious RMG developer, user, going to really engage with RMG, you should attend the green ones, which are about kind of more advanced stuff. Some applications are discussed in the red things in the videos. And there's some specialized lessons. If you're interested in big macromolecules, or if you're interested in catalysis, these are kind of specialized lectures about those particular applications. All right, that's all I have. Have you any questions?